Hi everyone. Today let's talk about session 1.3, conditional propositions and logical equivalence. Conditional propositions. If it is raining, then the sidewalk is wet. So what is P and what is Q? So P is the statement, it is raining. Oops, let me change to the other color. Do you like purple? Okay, so we have it is raining. Oops. Okay, Q is the sidewalk is wet. Okay, then this statement is if P then Q. We use the symbol P implies Q. Okay? So let's look at the next sentence. If you become my friend, I will give you candy. Oh, looks like my daughter will say that. So in this case, what is P? So P is you become my friend. I will give you candy. This is Q. So this is P implies Q. Okay, so this is conditional propositions. What is the truth table? So think about this is the truth table. Remember the left-hand side is going to be the same as we learned before in our last class. So P and Q, each of them can be true or false. So each of them has two choices. So we have P and Q, two positions. So 2 times 2 is 4. We have 4 different possibilities. So P can be true, true, false, false, and Q is true, false, true, false. And then those are the 4 possibilities. Okay. So true implies true. That's good, right? So yeah, remember it's like if this is true and then that is true. So this is good. Next, if this is true and then the conclusion is false, well, this is not good. Okay, so true implies false is false. Okay, how about if P is false? Well, if P is false, then we will consider this implication is true. Okay, because the hypothesis does not satisfied. Okay, so no matter what the conclusion is, we think this conditional proposition is true. So according to this truth table, we can think true implies false is false, and then all the rest are true. Okay. Next, keep this in mind. Let's complete the following truth table. So now we have P, Q, R, 3 propositions. So let's look at the first. We have P or let's look at the order. So we first compute P or Q, and we compute not R, and then we compute the implication. Okay. So P or Q. So true or true is true, right? And then not R. So R is true. So not R is false. True implies false is false. So this guy is false, right? Next. Do you see actually all of these is true? So true or whatever is gonna be true. So this is true on the left. And then the R, not R. So when R is false, not R is true. True implies true is true. True implies false is false. True implies true is true. So far, so good, everybody. Okay, next. P or Q. So false or true is true. Not R, not true is false. True implies false is false. Okay, if the hypothesis is true, the conclusion must be true. Okay, this is the implication. And then next we have false or true is true. Not false is true. Oh, this is good. False or false. Oh, you can see both of them, false and false give us false. And false implies whatever does not matter is gonna be true. Like this. Remember, like this? False implies whatever is true. Okay? Alright, let's continue. We have P and Q implies R. P and Q. So, true and true is true implies true is true. True and true is true implies false. Oh, that is false. So I strongly recommend you to try to fill in this truth table first, and then you continue to play the video and check your answers. Okay, in this case, you can have more chance to practice and learn. Next, true and false is false. And true and false is false. And because it's false, false implies whatever is gonna be true. And actually all of these, because it's false and whatever is gonna be, so false and whatever is false, right? And then false implies whatever is gonna be true. So all of these are true. So far so good, everybody? So, if you get this like small strategy, and then it can help you to speed up the answering process, right? Okay, and then next this logical statements, we're gonna compute Q implies R first, and then we compute the AND. Q implies R. So Q implies R, true implies true is true, and P is true. Oh, so the answer is true. And here you can see all these, the P is true. And then Q implies R, true implies false is false. And then when Q is false, false implies whatever is gonna be false. Sorry, it's true. Sorry, I said it wrong. How do we get this? Because false implies whatever is gonna be true. Okay? And then true and false is false, true and true is true. Okay, so we get this. And the rest, do you realize the P is false? And false and whatever is gonna be false. So that's why we know all these are false. Okay? Alright, let's continue. P implies, so here the order we should compute Q implies R first. So Q implies R, true implies true is true. And then P is true. So this gives us true. And you can see all of these P is true. And then this guy, true implies false is false, and then true implies false is false. And then QR, false implies true is true. Alright, same thing. False implies whatever is gonna be true, and then true implies true is true. Next, do you realize is false? False implies whatever is gonna be true. Okay? Yeah, we don't need to figure out like Q and R as long as P is false. False implies whatever is gonna be true. Okay, everybody? So, yes. That is the truth table. Okay, so if P then Q, we say P is a sufficient condition for Q whenever the occurrence of P is all that is needed for the occurrence of Q. Okay, so P is the sufficient condition. Okay, Q is a necessary condition for P whenever P cannot occur without the occurrence of Q. So keep in mind, P implies Q. Then we say P is the sufficient condition and Q is the necessary condition. Okay. All right. Example. Write each proposition in conditional proposition form. Okay. First, Betty will be a good student if she study hard. Okay, you do see the if. So it means whatever proposition after the if, that's our P, okay? So if we change the order, we should say if she study hard. But what is she? Because we mentioned it for the first time, we should say if Betty studies hard. Then the Q. Betty will be a good student. So here we can use she. She will be a good student. All right. This is the first one. Second one. When you sing, my heart will be warmed. So when you sing, it's like if. So if you sing, then my heart will be warm. Okay. Next, a necessary condition of you getting a good grade is that you read each session we cover. Good tips. Okay, so necessary condition is the Q. The Q is this guy. So this is the Q, and the P is you getting a good grade. So let's put this sentence down. If you get a good grade, then you read every session we cover. Okay, so this is number 3. Number 4, a sufficient condition. Sufficient condition is P, right? So sufficient condition of the Q is the P. So the P is taking calculus. Okay. So if P, who's taking calculus? You. If you take calculus, then Q. Being in a mathematics class, then you are in a math class. So far, so good, everybody? Okay, so keep in mind, P is the sufficient condition. Q is the necessary condition. Okay, let's continue. Converse statements. If it is raining, then the sidewalk is wet. P implies Q. Okay, the converse statement. So converse statements means we just switch the P and Q. Okay, so the converse statement is going to be Q implies P. So we switch the prepositions. So the converse statement is the sidewalk is wet. Then it is raining. Okay, so this is Q implies P. Okay, so next, bidirectional propositions. If P and Q are propositions, then the propositions P, if and only if Q is called bidirectional propositions. So if and only if. So P if Q, it means, so if means if Q, then P, okay? Only if Q means, so only if means P implies Q. So PQ is the necessary condition, okay? All right. So for bidirectional statements, it means P and Q are equivalent, right? So only if both of them are true, then the result is true, and both of them are false, then the result is true. So only if the true and false, they must be the same, agree, and then we get true. Otherwise, it's gonna be false. Okay? So same is true, okay? Different is false. Okay, next is the statement 2 less than 3 if and only if 4 equals 8 minus 4, true or false? Okay, now let's see. 2 less than 3, is this true? Yes. 4 equals 8 minus 4, is this true? Yes. So false if and only if true if and only if true is true because they're the same. Okay, so this is the bidirectional propositions. Next, contrapositive. If it is raining, then the sidewalk is wet. The contrapositive statement is gonna be not Q implies not P. Okay, so we're given P and Q, so P implies Q. The converse is Q implies P. The contrapositive is not Q implies not P. Okay, so not Q. So this is P, this is Q. Not Q means the sidewalk is not wet. Okay, and then, so, we forgot the if. And then, P, not P, right? So it is not raining. All right. So this is the contrapositive statements. If not Q implies then not P. Okay. Oh, I just realized last time we also forgot the if. Okay. All right, let's continue. Equivalence logical propositions. If two propositions have the same truth values in a truth table, then the statements are considered equivalent. Okay, so to indicate that two logical propositions are identical, we use the symbol, these 3 horizontal line segments. So 2 horizontal line segments means equal, and then the 3 horizontal line segments means equivalent. Okay, suppose P and Q are logical propositions. If they have the same truth values, we say they are equivalent. Okay? So notice that the truth of proposition does not necessitate the truth of its converse. Yeah, so if P implies Q is true, it doesn't mean that Q implies P is true. If we look at the truth table, let's see. If we look at the truth table, I don't have enough space here. So, okay. Let's do it here. P, Q, P implies Q, Q implies P. So P is true, true, false, false. Q is true, false, true, false. Okay. And then, next, we have P implies Q is only false when P is true and Q is false, and then the rest we have true. And Q implies P is only false when Q is true and P is false. and the rest is true. So we can see they are different. So we know then P implies Q and Q implies P, they are different. Okay, they're not equivalent. Okay, next, a proposition and its contrapositive are equivalent. So actually P implies Q is equivalent to not Q implies not P. Okay, why is that? Let me see. We can also draw the truth table to show that. Okay, so can I move this guy a little bit? Okay, let me see. Yes, I can move this guy. So then I have more space here. Okay, so now sorry. Okay, let's continue. So not Q implies not P. Okay, not Q. So this is an implication. The implication is false only if this guy is true and this guy is false. So if not Q is true, that means Q is false. Okay, so Q is false. Not P is false means P is true. So if P is true, Q is false, so this guy, then we have false. And all the rest is gonna be true. So now you see, these two guys are the same. So that's why we know a statement, a proposition, and its contrapositive are equivalent. Okay. Next example, we can show the De Morgan's law for logic. Okay, so De Morgan's law for logic, do you remember last time we have the De Morgan's law for sets? Okay, what was the De Morgan's law for sets? So we have A union B complements equals A complements. Remember the complement is like the negative sign. It flipped the inequality, so it flipped the union to intersection. And then A intersect B complement is A complement. It flipped the intersection to a union. So this is De Morgan's law for sets. We studied that in session 1.1. So now it's for logic. So the not really acts like complement and the negative. So not P or Q is equivalent to not P. You also flip the or and, right? So or becomes and. So that is not P and not Q. Okay, so not P and Q is equivalent to not P or not Q. Okay, let's continue. All right, so this is the truth table. Okay, so let's use the truth table to prove it. Okay, for De Morgan's law for sets, we use the Venn diagram to prove it. But here we're not talking about sets, we talk about logic, propositions. So we use truth table to show their equivalence. Okay, so here we first compute P or Q. So true or true is true, and then not true is false. True or false is true, and then not true is false. False or true is true, not true is false. False or false is false, not false is true. And then we have next, not P. So we compute the not first and then we use and. Not P is false and false is false. And the next we have not true is false and not false is true, well, that is false, right? And then not false is true, true and not true is false, The last one, not false is true, not false is true, sorry, I say true. Okay, true and true is true. So far, so good, everybody. And you can see they are the same. So the truth table values are the same. Then those two propositions are equivalent. Next, P and Q. So true and true, true. Not true is false. True and false, false. Not false is true. False and true, false. Not false is true. False and false is false. Not false is true. Okay, next we compute not false, not P and then not Q, then we use OR. Okay, not P, not true is false, not true is false, false or false is false. Not true is false, right? And then not false is true. So false or true is true. Not false, true. Not true is false. True or false is true. Not false, true. Not false, true. True or true is true. Okay, so now you can see they are the same. So that's why they are logical equivalent. Okay. So let's continue. Okay. So I hope you can stop the video here and try to practice. Okay. So practice this. Okay. So here P implies Q. So P implies Q is only false when P is true and Q is false. Okay, so P is true and Q is false right here. So that's why this guy is going to be false, but not false is going to be true. But for the rest, P implies Q is going to be true, but not true is going to be false. So far, so good, everybody. All right, let's continue. Okay. Yeah, so usually when we think about it, we keep in mind that the only case that P implies Q is false is when the P is true and the Q is false. So keep this in mind. Okay, so next, P and not Q. So true and not true is false. Oh, this is false. True and not false is true. Oh, this is true. False. So false and whatever is gonna be false. And are they the same? Yes, they're the same. So these two propositions are logical equivalent. Okay, let's continue. So P implies Q is equivalent to, let's see, P implies Q. We know this is false only if P is true and Q is false. So this is false. All the rest is true. Okay, not P is false or Q is true. So this is true. Not true is false. False or false is false. Not false. Oh, actually here not false is going to be true. True or whatever is going to be true. So this is true as well. So far so good, everybody. Are they the same? Yes. They are the same. So that's why these two propositions are logical equivalent. And this proposition is so important. I want to highlight it. Okay, because this guy give us we can transform the problem from a conditional propositions into logical propositions only connect with not and or. Okay, and so this problem is very important. So keep in mind, P implies Q is equivalent to not P or Q. Okay. Similarly, now we can because P implies Q is equivalent to not P or Q. Okay, then Q implies P. Well, you simply just switch P and Q positions. Then you can have Q implies P is equivalent to okay, let me put it down right here. Okay, so we use the same formula, but we just switch the P and Q. So by that formula, Q implies P is equivalent to not Q or P. And it's the same as P or not Q, right? Just put P in the first place. Okay, so that is why when we combine them, so P if and only if Q, well, P if and only if Q is the same as, so this notation is the same as P implies Q and Q implies P. But P implies Q is equivalent to not P or Q, okay? And Q implies P is equivalent to P or not Q. So that's why you can put the and in the middle. So then we can see this guys, they are logical equivalents. So far so good, everybody. Okay, and this is sessions 1.3. And don't forget, if you have any questions, please print screen and ask me in class or office hours or email me. Have a nice day. Bye.